Okay, so today I'm going to go over position, velocity, and acceleration. And we're going to do this in a calculus base because this is a calculus based physics class. So the first thing I'm going to start out with is position. Now position is where something is. Okay, it's where it is located. But we usually deal with things that are like delta x, which is our displacement. And delta x is where we are at the end minus where we are at the beginning. So if we had a little number line here, let's say -5, -4, -3, -2, -1, 0, 1. Okay, so I kind of skewed it toward the negative side. So let's say that we have our little person and they're standing here. This is their initial position. And let's say that our little person takes a walk and they go over here and they end up here. That's our final position. Well, the word displacement literally means moved from where you were. So here we are where we started, here we are when we ended. And so our displacement is going to be our x final minus our x initial, and our final position is 1. Our initial position is -5. So I ended up with a displacement of +6. Now it's whatever units this is in. It might be feet, it might be meters, it might be inches, whatever units this is in, that's what my units would be. But this tells me the positive says that its displacement is 6 meters, or 6 whatevers. Let's take the meters off. 6 to the right. Okay, now if I had reversed these two, if this was my initial and this was my final, then it would be -6 because I would go 6 to the left because displacement is a vector. Okay, now let's take that displacement and let's apply it to velocity. Velocity is the rate of change of position over time. And we can have a couple of different velocities that we can find. And the first one is our average velocity. Average velocity is change in position over change in time. Okay, which is, and I'm going to leave that as delta t on the bottom, and this is x final minus x naught. Really, we could write this as x final minus x naught over t final minus t naught. However, most of the time when we're writing this, we just do a delta t, because most of the time when we're timing something, we're just starting from 0. We're not starting from some, we're not saying, okay, I'm going to say go now at 30 seconds, and then when I stop, I'm at 45 seconds, and I got to subtract those two. But if you do, this is the appropriate way to write it. So let's say that our little person, so say our person did the move of 6 meters, okay, we're going to give it meters, in 3 seconds. Okay, if they did that, then their V average would be their change in position over their change in time, which would be that 6 meters over 3 seconds, and that'll be 2 meters per second. Our units for velocity are always distance over time. And so there's that. Now, I want you to notice something kind of neat though about this. Look at this. This is the change in something over the change in something. Okay, if we have an xt graph, then the rise would be delta x. The run would be delta t. And what do we know that rise over run is? Well, that's the slope. So the slope of a xt graph is velocity. that's kind of nice. Okay, so if I have some points and I plot a line and they ask me for what's my average velocity, I just find the slope of that line and there I am. But what if that line is not straight? What if that line is like this? Okay, if that's my xt graph, this is not a constant velocity because it's not a constant slope. But I could find the slope at some point. And so if I say, okay, what if I go down here and I take these really small time intervals from here to here and I find the slope? That slope's pretty close to that, right? Well, if I shrink that time interval down really small, if I find the slope of the what's called tangent line at a point, I find velocity at that instant, or instantaneous velocity. So v instantaneous is the slope of the tangent line. And if we've had calculus, the slope of the tangent line is the derivative of position with respect to time. So there's my instantaneous velocity. So I would take the derivative. Now, am I going to always use this on a graph? No. I might come up and I might have an equation like this. I might have something where they give me an equation or an expression. This would be an equation. So let's say that they give me an equation for position and it's 3t squared plus 2t. And that's my position. Okay, my v instantaneous would be dx dt. So we're going to take the derivative of this with respect to time. So 2 times 3 is 6t plus 2. And that would be my expression for velocity right there. And I could find it at any given point in time. I could say, what's the velocity at 1? And I could plug in 1. So that would be 8. What if I said the velocity at 2? Well, that would be 6 times 2 plus 2, or 14. So anything that I want to do, I'm just going to plug in that time, and then I could find those velocities at that given point in time. And you notice that like this one that I gave us would really be a pretty good fit to something like what I have here, because as time goes on, my velocity gets bigger and bigger. This slope is smaller here, but it's going to get steeper and steeper and steeper as I go up that line. So that makes sense. The last thing that I told you I was going to talk about today is acceleration. And acceleration, that's the rate of change of velocity over time. And so acceleration, and this is average acceleration, is change in velocity over change in time, which is v final minus v naught over change in time. So if I know the velocity of something in the beginning and I know something's velocity in the end, I can simply subtract those two and then divide. Again, we look at this. Rates of change. Rates of change. Rates of change are slopes. So if I have a velocity time graph and I find the rate of change of it, the rise is going to be delta v. The run is going to be delta t. And rise over run is slope. And delta v over delta t is acceleration. So the slope of a vt graph is equal to acceleration. So if I go and I calculate the slope of that graph, that's going to equal my acceleration. Now, of course, my instantaneous acceleration follows that same path that instantaneous velocity does. And instantaneous acceleration is where I shrink that time interval down really small. So maybe I have something that looks like this, but I want to know, hey, what is it right here? Well, right there, my slope looks like this. My tangent line slope does. And so my acceleration is going to be the derivative of velocity with respect to time. Now, remember that velocity is the derivative of position with respect to time. So I end up with d squared x over dt squared. And so acceleration is the first derivative of velocity, second derivative of position. Okay? All right. To go in reverse just a little bit from this, since velocity is the derivative of position with respect to time, I can separate my variables and multiply both sides by dt so that dx is equal to v dt. And then I can integrate. And over here I get delta x, and that's equal to the integral of velocity with respect to time. So this tells me, integrals, remember, are areas. So if I have a VT graph and it looks like, well, let's make it a straight line like this, then the area under that is delta x. Okay? If I'm given a function like I did before where I had, like, 3t squared plus 2t or whatever, if I'm given a function for velocity, then I'm going to integrate and go backwards from that. And since acceleration is dv dt, then I can separate those variables and I get dv is equal to a dt, and then we integrate that to find that the change in velocity is the integral of acceleration with respect to time. So delta v is the area under an AT graph. Delta x is the area under a VT graph. And that's position, velocity, and acceleration in a nutshell.